and welcome to the BigML tutorial series. In this video, we will be discussing datasets. We will begin with an introduction in which we will see how to create a dataset in the typical BigML workflow using a one-click action. Then we will discuss the primary purpose of datasets, which allow for data exploration and serve as a pre-flight check before creating models or other machine-learned objects. In the basic features section, we will see the other methods that are available for dataset creation, as well as how to create a training and test split for evaluations, and an additional data exploration tool. And then finally, in the advanced features, we will see how to filter datasets, and a quick example of how to engineer new features using BigML's domain-specific language called Flatline. So, what is a dataset? Datasets are the fundamental building block of all resources in BigML. Models, clusters, anomaly detectors, everything except sources derive from datasets. And speaking of sources, they can only create datasets. That is, once the field types have been verified in the source step, you will typically create a dataset, and all further analysis you perform will return to the dataset. You don't normally go back to the source unless you need to upload fresh data. As a fundamental building block, the integrity of the data in the dataset is important, and so the dataset view provides visualizations to make it easy to perform a pre-flight check. In particular, you can see a count of the number of missing values or errors that were found in the data, and the dataset view also provides summary statistics, so you can quickly review the nature of your data. As an additional safety net, the dataset server also marks fields that may not be useful for predictive analytics as non-preferred. This automatically removes them from further analysis. You can, of course, override these decisions. And one additional field setting that you can perform is a default objective for one-click actions. So let's take a quick look at creating a dataset. For this demonstration, we'll be returning to the Lending Club example. I already have this source created in BigML, so let's create a dataset using a one-click action. There are actually two places you can do this. The first is directly from the sources list that you see here. By hovering over the name of the source, a menu pops up in which we can select the one-click dataset option. Creating the dataset from here launches the process in the background. You can jump directly to the new dataset using the resource link here. Or, of course, you could always go to the dataset list and open the dataset from there. The second way to create a dataset with the one-click action is to use the option under the cloud action icon when viewing the source. So if I select this source and we look at the source view again, the cloud action icon has a one-click dataset option. Creating the dataset this way takes you directly to the new dataset. The dataset is computed in a streaming fashion, which means that you can see partial results as the computation is being performed. As with the source view, each field or column from the original data is transposed and listed in rows to make pagination through the fields possible. For each field, we can see the name and the field type from the source step. If we hover over the field type icon, we can see the field ID that BigML uses internally to identify this field. This ID functions as a canonical identifier for this field and is often useful when working with the API. The field ID makes it possible to freely change the field name without worrying about impacting previous or subsequent work. For example, if we decided that the loan amount field did not need the underscore in its name, we can change it. To do so, move the mouse slightly to the left of the field icon until a little pencil icon appears. This will bring up a window where we can change the name as desired, or even add additional metadata for this field, including a label, or even a full description. Once your changes have been entered, pressing Save will store this information into the dataset. This field metadata becomes part of the dataset and is carried along to all resources created from this dataset. For example, these field names will now show up in the tree visualization of a model built from this dataset. Further over in the columns, we can see a count of the number of rows this field contains, the number of missing fields that were detected, and the number of errors. These are typically caused by having invalid data, like having a string show up in a numeric field. And then finally, we have a histogram, which gives us a visual look at the distribution of the data. For categorical values, like the loan term, the histogram shows the counts for each class. So in this case, we can see that there are 16,053 loans of the class 36 months and 6,718 loans of the class 60 months. For numeric fields, like the loan amount, the histogram also contains a little hover icon that reveals your standard univariate analysis data, like the minimum, mean, maximum, and standard deviation. And for text fields, like the employment title, there's a little hover icon that brings up a tag cloud, giving a visual representation of the token frequencies that were discovered in that text field. In this case, we can see very quickly that there are a lot of people with manager in their employment title that are applying for a loan. The last thing to note about the dataset visualization is the little red exclamation points. This marks the field as non-preferred, which means that they are probably not useful for predictive analytics and will be ignored, for example, when creating a one-click model or other resource. The heuristic for determining the non-preferred status considers several things. In this case, we can see that there are two fields, the ID and the member ID, which have been marked. This is because, as IDs, they change too often and are not useful for discovering general rules about the data. Further down, we can see another field that has been marked as non-preferred, the title. This contains a short summary of the loan application as written by the loan applicant. In this case, what has happened is that the field type detected by peeking at the data in the source step was categorical. But when creating the dataset, BigML has discovered that there are far too many discrete values for this field to be useful, similar to the IDs above. We can see this also when looking at its histogram. Each one of these possible values is only occurring once or twice, or maybe at most 3 times. There are 2 ways we can fix this. The first is we can override the non-preferred status by changing the setting in the field metadata. As before, we click on the pencil icon, and there's an option right here that you can click on that makes this field no longer non-preferred. Once we've made this change, you'll see the red exclamation mark is gone, and this field will now be utilized as is in further analysis. The second way we can fix this is that we can change the field type. In this case, we could change the title to be a text field, which would allow BigML to extract the potentially interesting words the borrower uses when summarizing their loan application. To do this, we need to return to the source, configure the title field, and recreate the dataset. We can update and rerun the OneClick dataset. This is required because the dataset creation process relies on the field types that are defined at the source step to create the summaries. So you can only change the field types at the source step. And as you can see, now that we've changed the title to be a text field, it's no longer non-preferred. And we have something that's quite a bit more sensible in the histogram, where we have things like consolidation as a word occurring in the title 13,000 times, and credit card refinancing 4,859 times, for example. Now there's one more detail that can be changed in this field metadata, which is the default objective. So anytime you use one of these one-click actions, like a one-click model or a one-click ensemble, the default objective is the field which the model will try to predict. If you have not specified a default objective, then the OneClick actions will use the last preferred column. For example, in our lending club data, if we built a OneClick model, it would try to predict this last field in the dataset, this collections 12 months extended. We might prefer the OneClick modeling action to use, perhaps, the loan status, where we're going to try to predict whether or not a loan is charged off, current, defaulted, or fully paid, for example. This will give us a model which, based on the parameters of a loan, can predict if they will be good loans or bad loans. So to change the default objective to be this loan status, we once again open up the field metadata with a little pencil icon, and then click on this little target. Once we save the changes, this will now be the default objective for this dataset. So now let's take a closer look at the basic features of datasets. The first thing that is important to understand about datasets is that they are mutable. Previously, we saw how you can edit the field metadata, like the field name, the label, and the description. But it's important to understand that the actual contents of the data itself, cannot be changed once it is created. This immutability ensures that the canonical identifier, often called the resource ID, will always reference the same dataset contents, which is very important for repeatability, that is, being able to reproduce your results. At first, this may seem like a problem, since so far we have only seen how to create a dataset from a source. But you can also create datasets from datasets. So you can transform an existing dataset into a new one, for example, by sampling or performing a training and test split. It is also possible to create datasets from a batch output, for example, a batch prediction or a batch anomaly score. This means that the results from one machine learning workflow can feed into a new workflow. And finally, there's an additional feature for dataset exploration called the dynamic scatterplot. So let's return to the UI and take a look at these features of datasets. The first way to create a dataset with sampling is at the source step. So rather than perform the one-click option like we did before, if we open the Configure Dataset panel, we can see that we can change the sample size of the resulting dataset. So this is primarily useful when the size of your source exceeds the limits of your subscription. You can still upload sources that are bigger than your maximum task size, but in order to create a dataset, you would need to generate a sample within the limits of your plan. It is also possible to create a dataset by sampling an existing dataset. To do this, from the dataset view, we can choose the Sample Dataset option in the gears icon. Once this panel is open, the first option is the sample rate, which controls the percentage of the file to sample. By default, this will be a completely random sample. So if I set it here, I'll get a 50% random set of rows from this dataset into a new dataset. In the advanced sampling, it is possible to switch to a deterministic sample, meaning that a fixed value is used to seed the random number generator. This makes the sample repeatable. You'll always get the same sample when you do deterministic sampling. Using the API, it is also possible to specify a custom seed value. The next option is to sample with replacement. This allows for the same row to be sampled more than once, which is useful when you would like to make a sample that is different from the original, but is the same size, since rows will be repeated and others will be left out. So if I leave this at a sample rate of 100%, but I sample with replacement, I'll get a new sample that doesn't have all 100% of the rows, because some of them will be repeated. The Outofbag parameter flips the context of the rows that are being kept. For example, if we performed an 80% sample, and the Outofbag is set to no or false, This will give us the 80% sample that is in the bag. But if we set Outofbag to yes or true, this would give us the complement, or the 20%, sort of the other half of the sample, if you will. Of course, when sampling, it is possible that the field types or non-preferred status of the fields may change. So you can re-enable the auto detection of these actions as well. Now there is a special use for this Outofbag parameter, which is to create two complementary data sets. You might create one at 80%, for example, and another one at 20%. And the key is that they do not contain the same rows. You split a single data set into two new data sets that are sampled randomly but have no rows in common. And this is typically something you would do so that you can evaluate a predictive model. You would train on the larger data set, and then you use the smaller data set to see how the model is performing, making predictions on data that it was never trained on. And you could do this manually by setting the rate to 80% and changing this to deterministic sampling so that you get the same sample every time. Replacement no, so you don't double sample any rows. And then by having Outofbag no, you get the 80%, and by having Outofbag yes, you'll get the 20%. So you do this sample twice. But of course this would be somewhat tedious, and so we do provide a one-click method for doing this called the training and test split. So if you do the one-click training and test split, it will automatically do this 80 and 20% split for you. So after this one-click action runs, if I were to go back to the dataset menu, you're going to see that there are now two new data sets, the training set at 80% and the test set at 20%. Of course, if you would prefer a different percentage than 80 and 20%, perhaps 70-30 or 90-10, you can do this using the training and test configuration option under the gears icon instead of the one-click action. This will allow you to specify the percentage for the split, as well as specify a specific seed to use for the deterministic sampling. This makes your training and test set repeatable. So now let's take a look at the last two items in the basic features list, which are creating a dataset from a batch output and the dynamic scatterplot. So to do this next example, I'm going to switch datasets, and I will need to create a new source. And the source we're going to be using is the UCI diabetes dataset. And so if we take a quick look at this, what we have is a set of diagnostic measurements for female Pima Indians. And so we have things like the number of times they were pregnant, their 2-hour plasma glucose, their blood pressure measurement, etc. And then we have a doctor's assessment of whether or not they have diabetes. And from a predictive modeling standpoint, we could use this dataset to build a model that, based on these diagnostic measurements, tries to predict whether or not a given patient will or will not have diabetes. So from this source, let's go ahead and make our one-click dataset. And from the dataset view, we can go into the dynamic scatterplot using this dynamic scatterplot button in the upper left-hand corner. So what we can do now is we can put any two features we like on the X and Y coordinates. And then we can also change the coloration of this scatter plot as our third dimension. So for example, on the X coordinate, I could put perhaps the 2-hour plasma glucose. And in the Y coordinate, I could put the BMI. And we could color this by the diabetes category. So here we see now the blue dots are patients that do not have diabetes, and the orange dots are patients who do. And so we can right away see very visually that as your 2-hour plasma glucose increases, the rate of diabetes is increasing, and it's also increasing with respect to BMI as well. And in this visualization, this is a sample, and if we click this button up here, it will take a new sample. So this allows you to have a very interactive visualization for even very large data sets by visualizing just the sample. You can also zoom in on a specific region if you would like to see more detail about part of the scatter plot. And you can even fit a simple linear regression to the data if you like. And also you can see the Pearson and Spearman coefficients for the linearity of the relationship in these two dimensions. And this is a very powerful technique for seeing not only just the overall patterns in your data, but also sometimes you can see errors as well. And this dataset, in fact, actually has a great example of that, where if we look at, for example, the blood pressure, we can see there's a very large population of people. In this case, it's 18, as we can see in the data inspector over here, that all have a blood pressure of 0. And this is actually happening because these are patients that don't have blood pressure information, and rather than put in a missing value, they entered a 0 instead. But this could skew a model, and so you can clean this data set up and remove these zeros and put in actual missing values, and then the model will know to ignore the blood pressure for those particular patients. And this actually happens as well for the insulin level. There's an even larger population of people in this data set that have no insulin measurement, 237 people. All right, but one thing that might be interesting to do is to be able to look at the anomalies. Are there any anomalies in this data set, patients with anomalous diagnostic measurements, or as it relates to diabetes, for example, and be able to plot in this 2 dimensions which data points are anomalies and which ones are not. And so we can do this by returning to our dashboard, and we can build an anomaly detector for this data set. So we'll take the diabetes data set, and I'm just going to do a one-click anomaly detector. And once we have the anomaly detector, we're going to score all of the data points in the original data set using what's called a batch anomaly score. So this will take all of the data points in the diabetes data set and add the anomaly score for each data point. And the output is going to be a new data set. So let me show you how that works. From the cloud action icon, I can say a batch anomaly score. And as the input, I can just put the same diabetes data set again. And what you can see on the output is that we get all the same features we had before, but there's now this anomaly score that's being added. And when we process this batch output, one of the options will be to download it as a CSV, and the other will be to output it as a data set. And so you can see in this example, what's happening is we're creating a data set as the end result of a machine learning workflow. So we started with the data set, we created an anomaly detector, we used the anomaly detector to score all of the data points, and then we used that score to generate a new data set that is now amended with the score for each variable. So here is the score field that has been added to this data set. Okay? And we can, if we go back out to the data set list, you can see here's the original diabetes data set. And again, it's immutable. So the batch anomaly score data set that we just created is a brand new data set. But now we can put this into the scatter plot as well, and we can look at the same characteristics. So perhaps we'll do this again with the plasma glucose here and the BMI here. And so now in these 2 dimensions, the plasma glucose and the BMI, the coloration is by the anomaly score. So the bright green points have a lower anomaly score, as you can see in the data inspector. That data point there has a score of 0.38, which is fairly low. And the data points that are more red have a higher anomaly score. So we can see one up here that's slightly more red has a score of 0.53. And this patient up here, for example, which is clearly an outlier in this data set, is also marked and as an anomaly because they have an extremely high 2R plasma glucose and an extremely high BMI as well. But what's even more interesting is some of these anomalies that are hiding in amongst the regular population. And so if we zoom in down here and take a look at a couple of those, and so we can see this one data point that has a very high anomaly score of 0.63, even though there are several patients near them, right? They're not just an outlier. And this is actually an interesting case because they have all of these strong indicators for diabetes. They have a very high 2R plasma glucose. They have a very high insulin level, a very high incidence of diabetes in their family, the so-called diabetes pedigree. But this patient in this data set is actually marked as diabetes false, whereas all the other patients in this sample pretty much all have diabetes. If we change this back to the coloration by the class, you can see pretty much everybody in this sample, especially in this upper corner here, are all orange, meaning these are patients that do have diabetes. And here's this one person hanging out in here that apparently does not. And so this could be an error in the data. This could be the luckiest person in the world. But if they are the luckiest person in the world, it's not so good for your predictive modeling because the model needs to be able to generalize, and that data point isn't going to generalize very well. We can't all be the luckiest person in the world. And so here you can see one of the great values of being able to visualize with the dynamic scatter plot, but also the fact that the output of these machine learning workflows can generate data sets that can also be visualized. Okay, so let's finish this module by discussing the advanced features of data sets. And in particular, the 2 that we're going to look at are dataset filtering. So this is creating new datasets by filtering your existing datasets, and feature engineering, where we're going to create new fields in the dataset using the fields that are there. So we can take, for example, some polynomial expression or a discretization or something, but we can apply functions to our dataset to create a new dataset that has new fields in it. And to do this, we're going to return to the Lending Club example, and we're going to talk about the loan status. So you may recall that all of the loans that are in that dataset have mixed loan status. In particular, there were these 7 possible loan statuses. One is charged off or current, meaning that the payments are currently being made. Another possible outcome is that the loan is defaulted, it's been fully paid, or it's in a grace period, or it's been late for 16 to 30 days, or it's been late for 31 to 120 days. And if you think about this, this is mixed together loans that are still what you might call open and loans that you might call closed. What I mean is that we could filter this loan status and create a new data set that's just all the loans that haven't attained a final status yet, right? If they're current, payments are still being made. If they're in grace, or if they're any of the late categories, that's still a loan that hasn't finished. It hasn't defaulted or been fully paid yet. And similarly, we could filter out the loans that have reached a final state. Those are the ones that have been charged off or defaulted or fully paid. They're not going to go back to being current once they've been charged off or fully paid. Those loans are closed. And we might do this so that we could take the closed loans and try to build a model that predicts what the final outcome of all the loans that are in the open status are. So we could model the closed loans, and then we could use that model to score all of the open loans. So we take all the loans that are currently in existence that haven't attained a final status and predict what their final status is going to be. Now, when we do that, we don't actually care if it's charged off or defaulted. Those are just bad loans versus the fully paid ones, which are good loans. And so we would like to engineer a new feature that instead of having those 3 classes, it's just a some kind of quality measure where charged off and defaulted, well, those are bad loans, and fully paid, those are good loans. So this is the steps that we're going to perform with this Lending Club data set to explore the ability to do filtering and feature engineering. Okay, so we'll return to our original Lending Club dataset. And under the gear icon, the features we're going to be using first is the filter dataset. And this allows us to create filter expressions right in the UI. So I can filter by the loan status, and I can say equals any of these categories, and I can say, okay, if it's current, or if it's late, or it's in grace, or it's late even more. If it's any of those 4 statuses, then we're going to call this LC sample open. These are all the loans that are still open. They haven't attained a final status. And when I click Create Dataset, I'm going to get a new dataset that only contains the loans where the loan status is one of those 4 possible outcomes. So if we come down here to the histogram, we'll see again that we only have current and the in grace and the 2 possible late statuses. Now we can go back and filter this data set again to create the closed loans. So we would filter this data set. And again, we could filter by the loan status. But just for an example, we could filter by any of these fields. Like if we wanted to filter by the loan amount, we could do that. And there's different comparison options you can use, or equals options, or missing values. You can even do some statistics filtering where you can say, filter out the things that are between certain percentiles. All right, but to complete the example, let's go ahead and filter on loan status again. And we can go ahead and use equals again, that's no problem. And we'll take the fully paid and the default and the charged off. And these will be all the LC sample closed loans. And so now if I go back to my data set view, we're now going to have 3 data sets related to the Lending Club, the original and these 2 new, the open and closed. And much like the open loan, this one now will only have loans whose loan status are the statuses that we filtered for, the charged off, default, and fully paid. So that's how we can create new data sets by filtering existing data sets. And now let's perform this feature engineering step where we want to reduce these 2 classes of defaulted and charged off to just one field called bad, and these ones that are fully paid called good. So to do that, the option we're going to use is the Add Fields to Dataset feature, and this is where you can do this type of feature engineering. So when you're adding a field, of course, you can give it a name, and in this case, we might call this the quality. And we can see some of the operations that are built in. There's quite a few functions that are in here. There's some discretization, okay, if you had a numeric value that you wanted to treat as a categorical value, you could do this with discretization, so you could turn a numeric value into percentiles. You can also use built-in functions for dealing with missing values. If you wanted to replace missing values with a specific value, whether it be the fixed value, the maximum, the mean, lots of different options in here. You can do some normalization, okay, if you have numeric values that are of greatly different scales and you want to bring them all down into a common scale, you can do that with normalization and with z-scores. There's also some built-in mathematics functions like exponentiation and logarithms, square roots. There's some typecasting if you want to force a field to become another type. There's even random if you just want to try introducing some noise into your data set to see how that might impact whatever machine learning metric that you're experimenting with. There's some statistics functions in here where you can create new features that are based on the mean, the population, or the population fraction of existing features. And then there's something called S expressions, and these allow you to create little programmatic snippets in a domain-specific language called flatline. And this is a very powerful language that allows you to create new features in a programmatic way. And it's a complicated enough topic to be deserving of an entire module of itself. So I'm just going to give you an example of what's possible with these S expressions. And so in this case, what I'm going to do is I'm going to create an expression that gives us the string good when the field loan status is fully paid. And so I can do this by saying, okay, if, I can just write an if expression, the field loan status, all right, and now I need to make this a comparison. So I can say if this is equal to fully paid, then what I want to return is the string good. Otherwise, I want to return the string bad. Okay, and we actually have this little pencil icon open something called the flatline editor, where you can validate these expressions and make sure that they are correct. And it also does some syntax highlighting. And so one of the things you can do in this editor is you can validate this expression. And you can see it tells me I have a mistake. I have basically an extra closing parenthesis. And so I can correct that mistake and I validate it again. And now it tells me this expression looks good. And I can actually see a sample of my data up here. And if I hit preview, it'll actually apply this little function to my data. And I can see a sample of what the expression result would be. And so in this particular case, we can look at the loan status, which will be the last column in the data set. That's where these new fields go by default. And so we can see, for example, that this loan would have a loan quality of good, and this was a loan that was fully paid. All right, and similarly, we can see a loan status. We have to go a little further down to find one's bad. So here's one that's bad, and we can see this is originally had a loan status of charged off. So it's taking this loan status field, and for every row, it's looking at the value that's there, and it's comparing it to the string fully paid. And if those match, it's creating this new field that returns the value of the string good. And if they don't match, then it returns the string bad. So we can accept this, and this expression is correct, so we can hit create dataset. And now we'll apply that expression to every row in the data set. And the end result is we have a new data set that has a new field in it called the quality, and we can see it's exactly what we wanted. Now there is one more example of sampling a data set, which I didn't mention before, which is that you can of course remove fields. So at any of these steps, like going from a source to a data set or going from a data set to a data set, you can deselect fields. And so in this case, that might be something we want to do because the quality is very similar to the original loan status. And if we try to build a model right now that predicts quality, it's probably going to use the loan status because it's going to detect that when a loan is fully paid, it's good. And so we don't want this loan status in here anymore. And so we can actually sample this data set. And by default, it's 100% sample. So we'll just ignore all those settings. And we can just come down here and take out the loan status by just unchecking the box. All right, and now when we create this full sample, we have all the rows, but we're just leaving that one feature out. And so now we have exactly what I promised. We have a new data set which is the closed loans, with the new feature, which is just whether the loans were good or bad. And we also have the filtered data set of all the loans that haven't attained a final status. And now it would be a very simple matter to just do a one-click model, for example, and then use that model to score all the loans in this open data set. Although, I will warn you, if you are playing with Lending Club, please don't use that as investment advice. There are a few more tricks you need to do, especially because this data set has unbalanced classes, but that is something that will be addressed in the modeling module. Okay, so in summary, we've seen that the functional purpose of datasets is that they are these fundamental building block of all resources in BigML, and that they serve as a pre-flight check by giving you counts and histograms and the dynamic scatterplot, so you can validate your data and make sure that it is distributed the way you expect before you begin the modeling process. And then we went through several different ways that you can create a data set from a source using one-click and sampling, using a training and test split so that you can do an evaluation of a predictive model, from a batch output like a batch prediction or a batch anomaly score or even a batch centroid for clustering, and from a data set using sampling, filtering, or flatline to create new features.